So I'm Cao Yixin, an assistant professor from SMU. So welcome to listening to my talk. Today I want to share some recent progress on trustworthy natural language processing with knowledge guidance. And I will talk about the recent advance of large language models and if we need knowledge graph and how to combine them. Okay, so we just talked about large language model are becoming omnipotent, right? So with more and more parameters, with more and more data involved, large language model outperforms human in many tasks. So from the bird base with 100 million parameters to the T5 with 11 billion parameters to the current recent GPT-3 with like 200 billion parameters. So you really difficult to tell which text is generated by machines and which text is generated by human. And also the large language model read much more text corpus than human, maybe than any living human in the world. And with so much reading capacity, they have many emergent abilities. And here, okay. So here are some examples for their amazing emergent abilities. So first one is for long distance instruction understanding. So I try to give some instructions. So answer today is a nice day for my third questions. So you can chat with him or her. And with some questions or maybe some chit chat like hello or hi. And after, and it, at the third question, it still remember your instructions and will reply with today is a nice day. So really amazing long distance instruction understanding. And researchers attribute these abilities to the instruction tuning. So instruction tuning means that not only we provide the data for specific task, the language model to capture the patterns, to learn how to solve the tasks, but also you will provide additional instructions. What is the task for? So it's like learning to learn, which will be on top of the in-context learning to learn specific tasks and patterns. Also, there will be a reinforcement learning with human feedback. So it basically align the answers with human preference to select which do you prefer for the answers. And the second example is for amazing math reasoning abilities. And this reasoning ability actually we didn't expect, but surprisingly it just appeared. So because my kid is just in primary school, so I tried a lot of primary math and I found, okay, not only it can successfully solve the questions, but also give a very elegant solution reasoning process. And also there are some researchers conduct the GPT series large language models on arithmetic reasoning. So you can see it's the absolute performance is nearly 100. Really great and outperform the fine-tuned model. Note that the fine-tuned model is specified for a specific task, but the large language model don't need to train, but generalize well. And that's the second examples for the reasoning ability. And the third ability is for the massive fact memorization, which is referred to the previous question. All the knowledge, fact knowledge are stored in the large language model parameters. So here are two examples. So you can ask medical terms. So what is a hypertension? So it will know this is medical term refer to some high blood pressure. Also, we can ask some geographic facts. So what's the distance between Chicago and Tokyo? So it will give you exact, the correct distance is 6,000 miles. And in the below right bottom corner, it's a figure from the recent research paper. So you can check the x-axis is the popularity of the facts. And the y-axis is the accuracy, how the large language model performs. And there will be two types of language models. The blue one is the vanilla language model. The orange one, so we retrieve some related documents and as the input to the language model. So it's called retrieval augmented language model. So you can see if the knowledge is less popular, so you didn't see the knowledge again and again. So retrieval augmented language model performs good. But if the knowledge is popular, language model is fine. So again, let's conclude. Three amazing magically appeared large language model abilities. So the first, instruction understanding. The second one, reasoning ability. And the third, massive fact memorization, right? So really, really good. And so a very straightforward is, can we use large language models as knowledge source? So here is a recent paper. So use large language model as knowledge source. So usually when we solve some question answering problem, given a question, we just rely on the Wikipedia search engines to retrieve some related documents. And with the related documents, we just extract the answers to answer the questions. But now we can revise this pipeline to generate then read pipeline. Instead of retrieval, we just use the large language model to generate the related documents and then retract the documents. And our recent works, the first work is also following this direction. But we are not only to generate the background knowledge, the related documents, but also we to generate the reasons to solve the task. So we have 3 steps. The first one we call is code FND, so code-based few shot fact checking. So we are inspired by the chain of thoughts in the left side. So not only we provide some examples with the detailed reasoning process, the green colored text, but also we want to decompose the question into some simple ones. So in the right side is our model, first step model. So first one, we used some code-based prompts, and we omit some demonstrations. So I want to show some outputs. Basically, the bottom side is our output. You can see given the input, claim, leave from the White House in rainbow colors, 100 people, blah, blah, blah. And the large language model can automatically decompose the questions. So sub question 1, sub question 2, and it will focus on the related entities, events of interest. And then it will generate the sub-answers 1, sub-answer 2, the background knowledge. And also, given all this relevant evidence, it tries to give the reasons why it returned the later result as true. So you will see the reasons the White House has been illuminated with rainbow colors in the past to show support for LGBT community and their fights for equal rights. Okay, so that's how we use the large language model and as our first step. But actually this the performance is not as good as the fine-tuned model. So how to improve it? Because we cannot access to the parameters of the large language model. So the second step is we want to combine the large language model and the small language model. Not that small. Okay, so the second step, we want to turn the code FND into a inference only. So we gave in the top is our instruction. So you see, we provide the results. And given the results, we can see we want the code FND focus on the generate the related documents, the backgrounds, and the reasons only. So it can improve the performance. But how can we get the results if we want to predict the results? So it's like a circle, right? So, but there are three strategies. We can provide the ground truth on the training data with some corruption, and or we can use some other predictions from the baseline models. We can use some random generated tag results actually. And that's given the generated background knowledge and the reasons, that's our third step. So we want to include some social signals, how the news, how the fact spread over the social network. So it's a very general pipeline, so not very specific for this task. Given the code FND, we generate the backgrounds and the reasons, and then concatenate with the news articles. We feed them into an encoder, and the encoder will be a small-scale language model, and we will obtain the news embeddings. Also, similarly, given the heterogeneous social graph, we use some structure-aware multi-handed attention and to preserve such structure knowledge into user embeddings and publisher embeddings. And finally, we combine them together for the prediction. So so here is the preliminary results. We can see the blue bar is the baseline model. The orange bar is our model without the generated backgrounds and the regions. So you can see they are competitive, not much difference, but with the generated background knowledge and the reasons, the gray bar improves a lot. Okay, so we are not actually care about the performance, we care about the case. So why it boosts the performance. So on the top, the first one, we show a successful examples. The claim is Steve Jobs was adopted. His biological father was, I don't know how to say, Syrian Muslim, and the result should be true. And we can see ChatGPT generate a reason and give the background knowledge why the claim is true. But since we let the ChatGPT focus on generating the backgrounds and the reasons only, we provide the results, and sometimes the results are incorrect. So let's see some corrupt results given to the large language model and what will happen. So same claim. If we corrupt the result as false, it still gives some reasons. So it will say Steve Jobs was not adopted. So this is the reason why the claim is false. And if we corrupt the results as unverified, it still gives a reasonable reason. So we don't know if Steve Jobs was adopted or not. Amazing, right? Very amazing instruction understanding ability, even if the instruction is bad, right? So that's a problem. That's some issues come into our mind. Can we trust the parameterized knowledge? So here are some other examples. First of all, factor errors. What's the distance between Harbin and Singapore? In the early examples, we showed a successful fact memorization case, but here is the error case. That's the popular fact. Here is not that popular fact. What's the distance between Harbin and Singapore? So it's give a wrong answer. And for the medical misdiagnosis examples, the middle case, we know the ChatGPT understand what is hypertension. It's some disease for high blood pressure. And here I want to ask a more difficult question. Can I take midodrine for this high blood pressure disease? And he know the midodrine is a medicine that used to treat hypotension, a disease of low blood pressure. But you can see the ChatGPT suggests it can sometimes be used to treat the high blood pressure. So what will happen if you got a high blood pressure and you take some medicine to increase your blood pressure? Really, really bad, right? Maybe if someone believes this, maybe that's right. So the third is for the reasoning ability. Please do the analogy A, D, B, C, E, H, F, G, and what will be the letters for I, L, J, K, and still give the wrong answer. So you can see, even if we give even if it has a very good instruction learning understanding ability, but it trusts your instructions. The large language model trusts your instructions, even if the instruction is bad, is evil, is not correct. And it tries to meet your requirements. And even if the large language model can memorize a lot of facts, but it may make some errors, maybe sometimes to make very, very bad results. And even if it have some amazing reasoning ability, but not very strict reasoning, not very sound, not very valid. Okay, so here is our claim. If large language model are becoming Superman, help us to beat the evils. So sometimes we call Watchmen, right? In the DC comic movies. So our claim, who watched the Watchmen? So how can we trust them? So another type of model, knowledge graph, comes into my mind. So I'm not going to introduce what is knowledge graph in the workshop, but I will focus on the knowledge graph is an infrastructure of machines to explore knowledge. Is the foundation of the internet to organize resources. HTML, that's a type of knowledge graph, right? But not annotated with so many metadata, so not very powerful. So here I make a comparison between the large language model and knowledge graph. The first one is large language model is decisive, but knowledge graph is adamant. What does it mean? You can see from the early fact-checking examples, if we change the results in the instructions, even the instruction is incorrect, but large language model is easily swayed to give different reasons to meet your instructions. This is because anything inside the large language model with a probability, even if this is a fact, right? So it generates the facts sequentially, and its words over the vocabulary will have a distribution. So we don't know what will the large language model generate. But the knowledge graph mostly black and white facts. You see in this Wikipedia info box. So Singapore official language, English, Malay, Mandarin, and Tamil, and blah, 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 a lot of knowledge. If the knowledge is correct, so it will record this knowledge. If it's incorrect, it will not be included. So white and black. So 1 or 0, so no probabilities. And also knowledge graph have a photographic memory, never forget. The second point, we quote from the sentence from Steve Jobs. Large language model is hungry, knowledge graph is foolish. So what does I mean? Large language model always require more data, more parameters. This brings very good generalization abilities, but also bring another issue, learn new knowledge inefficiently. What do I mean? I just gave the examples in the panel. So what do you want to improve the large language model? Provide another additional annotations? Can you do that? No matter you gave like hundreds of annotations, thousands of annotations, it's so small compared with the pre-trained data, right? And what will happen for the knowledge graph? Even if you provide a piece of knowledge, the knowledge graph can update with it. It will memorize it. So knowledge graph will slow but steady learning each piece of knowledge. It learns actually efficiently for new knowledge. But large language model is inefficiently. So that's the second comparison. The third one is large model is black box. Input, output is okay, but we don't know why make such a decision and how to represent knowledge, although there are a lot of works to visualize the neurons, to give some theory to demonstrate the how the knowledge is represented with the parameters. But still, it's a black box, and we cannot control the parameters to intervene the knowledge. But knowledge graph is transparent. Each piece of knowledge in knowledge graph have ontology and semantic definition, right? and all the knowledge is visible to users. And also we have a long history to explore how to define the knowledge. We can exchange, we can update, we can store, and all this exchange, revision, imagine the Wikipedia will be stored in the history. You will know every updates, so it's trustable. So in conclusion, large language model is a statistical model, but knowledge graph is data model. So large language model learning from data, it is always struggling from forgetting and vs memorization. But knowledge graph systematically organize data and will gradually expansion via cross-sourcing. The knowledge graph can define with strict rules and ontology and specified in existing knowledge. But complementary large language model provide amazing fuzzy reasoning abilities with good generalization ability. So they are complementary. So how can we combine them together? So these are two challenges of combination. The first one, what type of knowledge graph is required? And the second one, what role shall knowledge graph play? So yes, the answer is correct. The existing entity-centric knowledge graph is not enough. We need more expressive knowledge graph, especially with the rapid development of large language model. So here are three types of knowledge that cannot captured by the current entity-centric knowledge graph. The first one is the complex knowledge. For example, so here is a video about how to clean kitchen, and there will be 3 steps: clean sink, wipe counter, and mop floor. How can we represent such a multimodal, such a procedure knowledge in the entity-centric triple knowledge? We cannot do that. And the second one is subjective knowledge. Given the same half bottom of water, and different people will feel differently, right? And the third type is the inferential knowledge, and this is to offer some reasoning abilities. So we need a more expressive knowledge graph. So event knowledge graph is a solution. So if you see this this graph, it's still some nodes, some edges, very similar to the entity-centric knowledge graph, but differently. Each event consists of several nodes and edges. It's a subgraph, and with this subgraph, it have more powerful expression abilities. It can represent various type of knowledge, such as the activities. It involves action with a duration, like run over, run around, walk and walk, and also can represent some accomplishment. Not only you make an action, but also you put some qualifier to them, like run a mile, and also some other types of knowledge, achievements, states for the subjective knowledge. But also, we should know that you can also, each node in the event knowledge graph can be either an entity or some literals, some text, some integral values. So it's more flexible. So here are some related works for the event knowledge graph. The first one is the concept net. So we all know concept net is a common sense knowledge graph. And each node in concept net is a phrase, short text. And we use concept net to empower the task with some logical consistency. So here is an example. So the second one related work is Acer. So it's another common sense knowledge graph, event knowledge graph, extracted from large corpus, but it focuses on like relatively fixed template, grammar template, like I have lunch, I have hungry. And if these two phrases are connected by some causal words like because, so it will generate a relation result between them. So again, each node here is a short text. So this is to alleviate the sparsity issues. So it can use to facilitate the co-reference in WIC co-reference task. So basically, they are given two questions. The fish ate the worm, it was hungry. The fish ate the worm, it was tasty. Very subtle difference. So, and we want to resolve what is it referred to. And we can retrieve the knowledge from the event knowledge graph and count the frequency and to solve what is the fish or the worm. The third is the COMET. So different from the first two related works, it's focused on the human everyday experiences. For example, the social interactions. What the person wants if the person is holding something in the water, right? So here is for the visual, for the image. So we can, from the image information, we can only see the person is holding something in the water, struggling. And given the COMET, the knowledge graph, so we will know before this what will happen, so what will lead to this, and what the person want to do. Okay, clearly the person want to survive. So based on these three works, we can conclude three challenges for the current event knowledge graph. The first one is large-scale ontology. So basically, existing ontology is a very small scale. For example, in the ACE 2005, there are only 6 types of events and 36 subtypes. But actually, this only provides low coverage of real-world happenings. The second challenge is fine-grained event structure. So basically, to alleviate the sparsity issue, each node in the event knowledge graph is represented as a short text, but actually we can decompose to a fine-grained structures because the structures actually defined by some ontology and is meaningful. The third challenge is multimodal events. So events as a very basic unit, semantic unit in the real-world happenings, it naturally bridges different modalities. And it have a strong expression abilities for the multimodal procedure knowledge. Okay, so here our second work about multimodal event knowledge graph. So we define such a knowledge graph in 3 levels. So in the right side is the multimodal context, including the images, the text, and then we parse them into the next level instance events in the middle. We do some processing, and then based on the parsed instance events, we make further abstraction. We induced concept events. So in this layer, we highlight this layer for the inferential knowledge. We want to conduct the common sense reasonings over this concept events. Okay, so how to build this multimodal event knowledge graph? So here is looks like a complex architecture. So I will not give very details. So we'll quickly go through it due to the time limit. So basically, there are 4 components. The first one, cross-modal event ontology. We need a unified, large-scale ontology, and then followed by textual and visual knowledge extractions. So that's a standard task. And finally, how to extract the relations between the events. So how to build a cross-modal, large-scale, unified event ontology? 3 steps. Because we want to exchange, we want to store the knowledge graph in a standard way. So we extend from the simple event model as the basic schema. And here is the extended schema. And yeah, so I just skip this. And then we follow the pipeline from top to bottom and then bottom to top to build and enlarge the ontology. First of all, to provide an initial ontology, we merge several high-quality knowledge graphs like FrameNet, WordNet, ImageStructure from the visual perspective. So on the right is the FrameNet. It provides some entity types like 1,400, like cause chains. It's very general and at the high level event types. Of course, there will be human annotated, very high quality core arguments, agent, entity, and non-core arguments duration, manner for each entity types. And then we want to go to some fine-grained event types by aligning the frame night with word night. For example, call change is very high level. Clean cause the room change. Stabilize cause the change to a stable states, right? So such detailed semantics, the hierarchical semantics, so you can find from word night. So we do some alignment. And then given the given the initial event ontology, and we just extract instance events and make some ontology induction. So here I will also skip the details because a lot of works here. For the textual knowledge extraction, basically information extraction. So it involves a lot of subtasks. Event detection, neighbor entity recognition, relation extraction, event argument extraction, relation extraction. Yes, yeah, I will not detail the detailed system. We have a complete pipeline for this, all of these tasks. Of course, we are developing the advanced system based on the large language model, and yeah, it will post to the archive like in a couple of weeks. And also the large language model opens another direction, open the opportunities for us to develop like a very general information extraction system. No need the ontology, no need the schema, and no need for specific task. We can solve it in one model. Yeah, and I think that's the big opportunities for us information extraction researchers. But also, of course, bring another challenges. Okay, so for visual knowledge extraction, I'm not familiar with this, but it also have some standard tasks: scene graph extraction, situation recognition. So we will leverage some also pre-trained models to recognize the event types and use some object detection to extract the raw information. So I think the next stage maybe will appear some multimodal or cross-model pre-trained models. So currently there are also some works to merge the pre-trained visual models, pre-trained language models together, and we will see a very strong, powerful abilities to extract both textual and visual knowledge. Maybe the GPT-4, maybe GPT-5. Okay, so here is our experiments. So this is the detailed evaluation for our knowledge extraction systems. So for text event extraction, we have two subtasks. First of all, for event detection, we convert into a mature word sense disambiguation task. So we can rely on some mature techniques here. And then for event argument extraction, and we achieve a state-of-art performance. So all these evaluations are based on the benchmarks. And now we apply our knowledge extraction system to several data sources. So you can see it's a very large scale data source, and we produce a large scale knowledge graph. So basically a lot of instance events, but more importantly, we have a largest concept events, because the concept events is a pure ontology to provide the inferential knowledge. Okay, so we also make some human evaluations for the extracted knowledge on the instance level and on the ontology level. So here we show two cases. On the taxonomy induction, we will see some positive examples. You can eat apple, but for the negative ones, you cannot eat table. And for the relations, for the positive one, so basically you destroy some buildings will bring some bad results like kill people. But for the negative ones, the destroyed building cannot invalidate some phenomenon. Okay, so next one, what role also, okay, so the first one, what type of knowledge graph is required? We need more expressive knowledge graph. Okay, and also we need some high quality knowledge graph. to provide a data model. And now, what role shall knowledge graph play? So here is our third work in the like last year CGIR. So we want to apply such event relation knowledge in the pre-trained language models. So we apply it in the future event generation task. So given the past events, the task is to generate a future event. So the idea is we want to highlight what the knowledge, such event relation knowledge, played a role in the reasoning, in the prediction. So in this task, we assume the knowledge will provide some psychology of the characters, and this psychology, the intention, the motivation, actually push the story forward, push the event sequence forward. So you can see, given the context, a family moved away to a new town, the current event, so the kid had to go to a new school. Before the next event, we want to understand what happens, what feelings about this character. He maybe get nervous to a new school, right? And so the next event will be she was nervous that she would not make any friends. Okay, so you see the event relation knowledge, provide some feelings, the subjective knowledge to push the events forward. So the conventional models just use the knowledge graph data and as the data to fine-tune the language model. But we think they contain different knowledge. So we have two separate models. One fine-tune on the inferential knowledge graph to provide common sense reasoning, and another capture the contextual information to generate the future event. And then we combine them via the prompt tuning. So basically, there are just two ways to combine the knowledge graph and the large language models, right? Just two ways. One is convert your knowledge graph into some low-dimensional encoding in the vector space. Another one is just let the large language model to generate some like actions to search over the knowledge graph. Okay, so here are our experiments. So on the top is the automatically evaluation for the task. So you can see for the automatically evaluation, we achieve a good performance, refer to the ground truth, the reference text. And what I want to highlight is the reputation and the distinction. We greatly improve the diversity of generated text because we understand the underlying psychology of the characters. And for automatically evaluation is not enough. I mentioned before, the evaluation is really challenging for text generation. So but currently the only thing we can do is the human evaluation. So at the bottom is the human evaluation. So we designed two tasks. The first task, whether the explanation is coherent with input preceding events. The second task, if the explanation provides necessary information for the next events. And you can see basically the X intent relation provides the most boost performance. So here two cases, one successful cases. Jack was taking his SAT test on Friday. He studied hard all week. On Tuesday, he was invited to a party, and the current event, he knew he should not, but he went to the party anyway. What's the future event? So basically, we want to say, okay, Jack did poorly on the test, right? But you see the current language model just generate he had a great time because he only know he went to the party, will have a great time. So given the explanations, we understand he will get nervous about the test. He will need to study. So the future event, we will generate Jack did not study for his task and he failed the test. And so, of course, we just failed in some cases. You see the first one, John was really bad boss. So we generate, he didn't know what to do. Actually, this is very general text. when the language model don't know the exactly reasons, the exactly background knowledge, we just say we don't know. Okay, so that's maybe we should increase the coverage of the knowledge. And also for the second and third cases, we can see the provided input is a motorcycle, but generated is the bike. The provided input is Europe, but the generated Mexico. So we also should include some factual knowledge into the event knowledge graph. So that will be hybrid knowledge graph in the future. Okay, so conclusion. First one, large language models are becoming omnipotent. So we can use large language model as knowledge source. But we want to highlight large language model are statistical model and knowledge graph are data model. So they are complement each other, right? Some drawbacks of large language model cannot be solved with more data and more parameters. Remember that? So given a new piece of knowledge, large language model will hungry about more data, more parameters. But knowledge graph will steady and slow learn each piece of knowledge. Okay, so but with the rapid development of the large language model, we need a more expressive knowledge graph, like our proposed multimodal event knowledge graph. And the last one, what role shall the knowledge graph play in the combination? So we actually provide a case to inject the event relation knowledge as the implicit character psychology beyond the data to push the event forward. So it's a joint reasoning. Actually, I was trying to talk about our recent work about continue joint reasoning about abduction, induction, and deduction. But actually, I just checked the policy, the conference policy. I cannot talk about that. Yeah. So so in the future, we need a high quality event knowledge graph, maybe with human in the loop, and we will need domain specific knowledge graph for expert large language model for some vertical domain. Okay, and most importantly, we want to use knowledge graph to watch the watchman, right? The large language model are so powerful, become our Superman. We want to watch them. So knowledge graph will be a very good source as evaluation and verification. And actually, we are doing that to provide a comprehensive evaluation as a challenge. And I think the challenge will be released in a couple of months. Yeah, so that's all. Thank you.